Everyone, today I will be talking class clustering instabilities and density of low frequency states in amorphous solids. Myself Prosenjit Das. Currently I am working as a postdoctoral research associate at George Washington University, Göttingen, Germany. My broad area of research is soft condensed matter physics and statistical mechanics. Mainly I worked in three different research areas. Number one is kinetics of phase separation, then dynamical properties of granular systems, and then mechanical properties of amorphous solids. Today, I will mainly talk about mechanical properties of amorphous solids. However, I will give you a brief overview of what I have done on kinetics of phase separation and dynamical properties of granular systems. So let us start with kinetics of phase separation. A system can exist in multiple phases depending upon external variables such as temperature and pressure. For example, water exists in three different phases. The solid phase of water is ice, the liquid phase of water is water itself, and the gas phase of water is water vapor. Also, a mixture of two immiscible liquid, let's say water and oil, they mix well when the temperature of the system is sufficiently high. However, they start demixing when you pull the mixture below a certain temperature, called the critical temperature of mixing-demixing transition. In kinetics of phase separation, we mainly study the evolution dynamics of a system, which is rendered thermodynamically unstable by rapid change of external variables such as temperature and pressure. For example, here in this picture, I am showing you melting of ice. The ice phase or the solid phase of water is stable inside a deep refrigerator, meaning that temperature and pressure inside a deep refrigerator is such that the favorable phase of water is the solid phase. Now, if we bring that solid phase out of the deep refrigerator and keep at room temperature and pressure, it starts melting. The reason is at room temperature and pressure, the favorable phase of water is the liquid phase. Now the question we ask in the context of kinetics of phase separation, how this solid phase transforms to the liquid phase. From the theoretical side of kinetics of phase separation, we model evolution dynamics of the system. Now, apart from theoretical interest, understanding phase separation problems are useful because of wide range of industrial applications, starting from metallurgy to material sciences to device applications. And in recent years, understanding phase separation in biological systems received enormous attention. These are the key problems I have done in this context. First, I have studied universality of domain growth in critical and off-critical binary alloys, which are useful in understanding ordering kinetics observed in metallurgy and material sciences. And then I have studied phase separation on pattern substrate like physically pattern substrate or chemically pattern substrate, which are useful in device applications. Let us now move to the second topic, dynamical properties of granular systems. Granular materials are ubiquitous. A typical granular system consists of assemblies of particles with size ranging from few micrometer to centimeter. Since the typical size of a particle in a granular system is relatively large, temperature doesn't play significant role in the dynamics of granular particles. So essentially, granular systems are athermal systems. When the granular particles interact, they interact via dissipative interactions. Meaning that they interact via inelastic collision or via frictional interaction. Because of dissipative interaction, they show many unusual properties. The example of granular systems are like collection of pebbles, bearing balls, food grains, etc. Here in this picture, I am showing you an example of granular system, which is just collection of pebbles. The first problem I have studied in this context is the freely evolving granular gas. A freely evolving granular gas shows clustering at the latest stage of evolution due to dissipative interaction, and also the velocity distribution of particles in the system shows deviation from the Maxwell-Boltzmann distribution. The question we ask in this context, how this cluster size grow in time, and also we characterize the deviation of the velocity distribution from the Maxwell-Boltzmann distribution. Next, I have studied shear-induced dilation in compact granular system. This work is motivated from natural phenomena like snow avalanches. So as you see, the propagation font of a snow avalanche shows dilation. Now the dilation observed in snow avalanches can be studied by studying a granular system. So what I have done here, first I generate a compact granular system by applying some non-zero pressure P to this upper surface made of red particles. Now keeping that pressure constant, I pull this surface with certain velocity u. Now in response to that pulling, the medium starts flowing. When it flows, it dilates. In the steady state, I have some average dilation, and then I ask question how that average dilation delta is related to pulling speed U and the intergranular dissipation parameter gamma for a given pressure P. In this context, we propose a scaling relation by balancing the rate of work done by the piston and the rate of dissipation by various dissipative mechanisms. So due to the positive time, I am not going into the details of this calculation. However, I will tell you the main result. When U is large, delta goes as U to the power 3/2, and dissipation dependence enter into this prefactor B. Now, when we extract the dissipation dependence, we found when gamma is small, like small dissipation, delta goes as U to the power 3/2, gamma to the power -half. And when gamma is large, that is large dissipation limit, delta goes as U to the power 3/2 and gamma to the power -2/3. So there is a kind of crossover. Now to validate our proposed scaling theory, so we perform numerical simulation, and this is the numerical data for average dilation as a function of pooling speed u for different decimation. Now to check the validity, what we do, we normalize this data by u to the power 3 by 2 and plot against gamma. So when gamma is small, this quantity decays as gamma to the power minus half as proposed in our scaling theory. When gamma is large, this quantity decays as gamma to the power minus 2 by 3 as proposed in our scaling theory. So our proposed scaling theory is in good agreement with our numerical data. Let us now move to the main talk. So this is the plan of my talk. So first I will give you a brief introduction to amorphous solids. Then I will talk about plastic instabilities in amorphous solids at temperature T equal to 0 and its extension to finite temperature amorphous system. Next, I will talk about density of low frequency states in amorphous solids at temperature T equal to 0 and its extension to finite temperature amorphous system. Finally, I will conclude my talk with a summary, and this talk is based on the following papers. So amorphous solids. Amorphous materials are ubiquitous. A typical amorphous system lacks long-range order that is characteristic of a crystal. Here in the left panel, I am showing you a portion of amorphous system. Here in the right panel, I am showing you a portion of crystal. As you see, the arrangement of atoms or constituents in amorphous system is irregular in nature, whereas in crystal, we have regular and repetitive arrangement of atoms or constituents, and that arrangement is long-range in nature. We don't see such thing in amorphous system. However, similar to crystal, amorphous solids resist external deformation by exerting internal restoring forces in the form of stresses. A typical amorphous system consists of assemblies of particles with size ranging from few nanometer to centimeter. Depending upon size, temperature plays significant role in the dynamics of constituents. When the size of the constituents are below few micrometer, temperature plays significant role in the dynamics of constituents. We call those systems thermal systems. The example of thermal systems are like metallic classes, polymeric classes, colloidal classes, etc. When the size of the constituents are above few micrometer, temperature doesn't play significant role in the dynamics of constituents. We call those systems athermal systems. And granular materials are example of athermal systems. And I have introduced to you about granular materials. Now, amorphous materials, especially metallic classes, are very useful in our many day-to-day life applications. For example, frame of rackets like tennis rackets or badminton rackets are made of metallic classes. Metallic classes are useful in many medical applications such as dental implants. Also, metallic classes are useful in recently developed 3D printing technology. Now, in all these applications, what is important is the mechanical stability of the material. So that motivates us to study the mechanical properties of amorphous systems. In this context, we focused on one aspect of mechanical properties, that is mechanical instabilities observed in this type of amorphous system. Now, instabilities in amorphous solids are also ubiquitous. For example, here in this picture, I am showing you cracks in a rock. This is an example from geology. Cracks in a rock appear when internal stresses become larger than the rock strength. Here in this picture, I am showing you an instability in a rod. So this is an example from our day-to-day life. And an instability in a rod appears when we apply elongational stress along its axis. In this picture, I am showing you failure in a bulk metallic glass. This is a picture from experiment. A failure in a bulk metallic glass appears when we apply compressional stress along its axis. In this picture, I am showing you failure on Earth, which arise due to earthquake, and this is an example from geophysics. Now, the important question related to this type of instabilities are the following. So, what is the nucleation process of an instability? What happens during an instability? What happens after an instability? And the most important question is, can you predict an instability? So, in this talk, I will mainly focus on question number 2, what happens during an instability? And question number 4, can we predict an instability? Like, can we develop a theoretical method from which we can say that an instability like this is about to occur? To study the plastic instabilities in amorphous solids at temperature T equal to 0, we consider a charged granular system in spatial dimensionality D equal to 2. Our system consists of frictionless elastic charged granular disk with radius Ri and charge Qi. When the two disks overlap, so they exert a repulsive force, which is given by the Hertzian interaction potential of this form. Here Kn is the elastic constant, R effective is the effective radius of two interacting disks, and delta is the amount of overlap, which is given by delta equal to capital Rij minus small rij. Capital Rij is the sum of the radii of two interacting disks, and small rij is the distance between the center of two interacting disks. Now, apart from this elastic interaction, because of the presence of charge, we have charge-charge interaction, which we have modeled by using damped truncated Coulomb interaction. As we are working in amorphous environment, the approximation involved here changes the result quantitatively, not qualitatively. Now, in charge granular system, one can induce plastic instabilities by applying external shear deformation or by applying external electric field, or one can apply both of them together. In the presence of shear strain and external electric field, the total potential energy or the total energy as we are working at T equal to 0 is given by this. So the first term represents the sum over all pairwise interaction, and the second term represents the contribution from the external electric field. So the question is, what is the motivation behind choosing such a complicated interaction potential? We know that in electrostatics, in charge-free region, del square phi equal to 0. So this equation preserves charges. Minimal excitation it allows is the dipolar excitations. Okay. But in elastostatics, we have del to the power 4 chi equal to 0. This equation preserves disclinations, which are monopoles, and dislocations, which are dipoles in the language of elasticity, but allows quadrupolar excitations. The minimal excitation we can have in this context is a quadrupolar excitation like this. So this is a picture we have generated by using computer simulation. Now the question is, how does the displacement field look like when we have both elastic as well as electrostatic interaction together? So that is the main motivation of using charged granular material. So first we consider the case A, where we apply simple shear deformation to the system in the absence of external electric field. This type of simple shear deformation preserves total area of the system. The additional displacement we impose to the particles or the constituents by applying simple shear deformation is called the affine displacement. By doing affine displacement, what we do, we basically change the distance of two particles in the system. Okay? Now, if we are in crystalline environment, before applying this simple shear transformation, in equilibrium, force acting on any particle is 0. And after this shear transformation, the force remains 0 because this horizontal bonds remains unaltered. This vertical bond elongates along this direction. This vertical bond below this plane elongates along the opposite direction. So they balance each other. The force remains 0. However, this is not the case when we are in amorphous environment. Force acting on any particle before applying this shear transformation in equilibrium is 0, but after this simple shear transformation it becomes non-zero because we do not have such symmetry present in the crystal. So the force that arises due to this affine transformation is called the non-affine forces. Now, keeping that shear fixed, if we allow the system to relax, particles in the system will displace themselves to nullify these non-affine forces. So the additional displacement that occurs to nullify these non-affine forces is called the non-affine displacement. Now, this non-affine displacement could be of two types. It could be elastic or plastic. Now, after equilibration, if we reverse the strain step and allow the system to relax, if the system exactly goes back to its previous configuration, then it is elastic. If it doesn't go back to its previous configuration, then it is plastic. Now, to study the plastic instabilities, we considered a charged granular system with two different type of grains, 50% of two different sizes of grains with their diameter ratio 5:7 and number ratio 1:1. 50% of small discs are positively charged, other 50% is negatively charged, and same is true for large discs. So effectively our system is charge neutral. As we are working at temperature T equal to 0, we deform this amorphous system in a quasi-static manner with a strain step delta gamma equal to 10 to the power minus 6. So basically what we do here, we apply a strain step delta gamma equal to 10 to the power minus 6 and allow the system to relax. We again apply a strain step and allow the system to relax and continues to do so. When it continues to do so, at some point we see rearrangement of particles in the system, and this is the plot of plastic displacement field. This type of plastic displacement field has also been observed in experiment on colloidal glasses by Chicardi and Shah. As you see, the displacement field is not quadrupolar, which I have shown you before. So this is different from quadrupolar. Now the question is, can we develop a theoretical method from which we can predict that a plastic rearrangement field like this is about to occur? Okay, so that is the most important question in this context. And the effect of such plastic rearrangement has also been observed in the measurement of macroscopic quantities such as stress component sigma xy, total potential energy or total energy of the system, and total polarization of the system. So in the upper panel, I have plotted stress as a function of strain. As you see, stress increases almost linearly when we increase the strain. So, however, this linear increase is disturbed by stress drop, which occurs due to the plastic rearrangement, which I have shown to you in the previous slide. Now, as we continue to increase the strain, at some points, stress ceases to increase, And after that, we say the system enters into plastic regime. Okay, and if we continue to increase the strain, at some point the material breaks. In the middle panel, I am showing you total potential energy of the system as a function of strain. This each energy drop is associated with a stress drop, and between two stress drop, the potential energy of the system increases as we increase the strain. In the lower panel, I am showing you total polarization as a function of strain. The total polarization shows this each polarization change is associated with a stress drop or potential energy drop, and the stress and the polarization change could be positive or negative, and that depends on the local environment. Okay. Now, if we look back this stress versus strain curve, this stress versus strain curve is piecewise linear. In the linear portion, the material behaves elastically, meaning that suppose we are at this blue point, if we increase the strain by some amount, okay, allow the system to relax there, the change in stress is same as if we decrease the strain by same amount from that point and allow the system to relax. The system exactly comes back to its previous to the point where we started. So basically, the system exactly comes back to its previous configuration. However, if we are at this green point, after the increase of strain by small amount, if the system undergoes a stress drop and we allow the system to relax here, then if we decrease the strain by same amount, the system cannot go back to its previous stress value. So basically saying the system cannot go back to its previous configuration. So that is the irreversible step or the plastic step. Now this elastic step or the plastic step can be easily understood by looking into the energy landscape picture. So here along y-axis, I have total potential energy of the system. Along x-axis, I have collection of coordinates. So as we are working at temperature T equal to 0, in equilibrium, the system stays in the potential energy minimum. When we increase the strain by some amount, the potential energy of the system increases. But if the system essentially remains in the same potential energy minimum, then if we decrease the strain by same amount and allow the system relax, the system goes back to its previous configuration or the previous potential energy minimum. So basically this path is reversible. So in the reversible step, the system essentially remains in the same potential energy minimum. So if we continue to increase the strain, at some point this potential energy minimum disappears. After that, if we increase the strain by infinitesimally small amount, the system moves from this vanishing potential energy minimum to the next potential energy minimum. When that happens, a plastic rearrangement occurs. After the occurrence of plastic rearrangement, if we decrease the strain by same amount, the system cannot come back to its previous configuration. So that is the irreversible step or the plastic step. Now, from mathematical point of view, when the system is in equilibrium here, double derivative of potential energy with respect to particle coordinates is positive. As we increase the strain, this potential energy landscape starts flattening out, meaning that double derivative starts decreasing, and it approaches to 0 when we approach close to a plastic rearrangement. Now, for many particle system, that double derivative is nothing but a matrix. We call it Hessian matrix. When we diagonalize this matrix, we get set of eigenvalues. One of the eigenvalue approaches to 0 as a function of strain when we approach close to a plastic event. Okay. Here in this picture, I am showing you first eigenvalue. So here we arrange the eigenvalues in ascending order. So first eigenvalue is the minimum eigenvalue as a function of strain. First eigenvalue approaches to 0 close to this point. So a plastic rearrangement occurs somewhere close to this point. When we are far from this plastic rearrangement point, the system is in equilibrium in a potential energy minimum. So the eigenvalue is positive, and that eigenvalue starts decreasing as we increase the strain. So which we have discussed in the previous slide, and it approaches to 0 close to a plastic rearrangement. After the occurrence of plastic rearrangement, the system moves to the new potential energy minimum where the system is stable again. So the eigenvalue becomes positive again. Now, when one eigenvalue approaches to 0, it has a nice consequence. To understand that, we have to do some mathematical analysis. So what I wrote here, that the derivative of force with respect to strain is 0. On any particle J is 0, because we minimize the potential energy of the system before and after applying a strain step. Now we rewrite this force in terms of the potential energy, total potential energy, and then we apply chain rule to this derivative, and this is what it looks like. Now this first term has only one index J, and it has dimension of force. So this is nothing but the non-affine forces. And the second term here, del 2u del ri del rj, has two index I and j. So it is a matrix. So it is nothing but the Hessian matrix, which I have shown in the previous slide. And dri is the displacement that solely arises due to the strain step. So this is nothing but the non-affine displacement. So we wrote it dy over d equal to 0. Our task is to calculate the non-affine displacement. So this is what it looks like when we rewrite it. Okay. Now what I am going to do, I am going to rewrite the inverse of this Hessian matrix in terms of the eigenfunction of the Hessian itself. So when I do that, this is what it looks like. Now this equation tells that the non-affine displacement field can be expressed as a linear combination of the eigenfunctions of the Hessian with a prefactor that is inversely proportional to the associated eigenvalue. Suppose pth eigenvalue approaches to 0, so most of the contribution or the amplitude of the prefactor will be very large for this pth eigenvalue. Okay, so essentially we can say that the pth eigenfunction will describe the non-affine displacement field. Here first eigenvalue approaches to 0, so we expect first eigenfunction will predict the non-affine displacement field. Here I have plotted first eigenfunction psi by black arrows and the non-affine displacement field u by magenta arrows, and the coefficient of agreement between the two fields is given by the magnitude of dot product of two fields, which is 0.994. So they are 99.4% accurate. So what we can say that first eigenfunction predicts the non-affine displacement field. So here actually I have two plots, and they are in good agreement, so that is why they are indistinguishable, and that is the main result. And again, if you see this displacement field, this is not quadrupolar in nature, so it is different from the quadrupole which I have shown in the few slides back. And we fail to understand how much it is quadrupolar and how much it is bipolar. Okay. After that, we have studied plastic instabilities in the presence of external electric field without any external shear. In that case, we looked at stress component sigma xx, sum of elastic energy and electrostatic energy, and x component of polarization. And further, we have studied plastic instabilities at fixed external electric field Ex equal to 0.5 and with increasing strain. In that case, we looked at stress component sigma xy, sum of elastic total potential energy of the system, and x component of polarization. In all cases, we see qualitatively similar result, meaning that close to a plastic instability, one eigenvalue of the appropriate Hessian approaches to 0, and the eigenfunction associated with that eigenvalue predicts the non-affine displacement field. Okay. Now the question is, how does that do you see sharp stress drop when we deform an amorphous system at some finite temperature? So that is the next question we asked. To study the plastic instabilities in amorphous solids at temperature T less than Tg, we consider a amorphous system in which constituents interact via inverse power law potential with power law exponent 2. We chose density of particles in the system to be 0.76. That gives rise to a glass transition temperature Tg equal to 0.3, and our working temperature is T equal to 0.1. That is 1/3 of Tg. As we are working at finite temperature, this is the typical trajectory of a particle in the system. A particle stuck in the cage formed by its neighbor. So basically, a particle performs chaotic motion inside the cage formed by its neighbor. Now, if we time average this trajectory over certain time tau, we can define a time average configuration. And our claim is that time average configuration is stable up to our observation time tau, provided tau is sufficiently large, and at the same time, tau should be sufficiently smaller than the typical relaxation time or the diffusion time of the system, so that this cage structure remains intact. Now, if we deform this amorphous system at finite temperature T equal to 0.1, this is the typical time average stress versus strain curve for the system. So similar to 0 temperature, we have sharp stress drop even at finite temperature. Now the question is, can we use the 0 temperature Hessian method to study the plastic instabilities at finite temperature T not equal to 0? Now we start with this 0 temperature Hessian, but it provides negative eigenvalues at instantaneous positions because the instantaneous positions are not energy minimized. So it failed to give structural stability related information. And then we compute this quantity at the time average configuration. These time average configurations are stable, but it also provides negative eigenvalues. The reason is these time average configurations are stabilized by an effective interaction potential, not the bare interaction potential U. And that effective interaction potential involves many body interaction because of the presence of collision at finite temperature, and we do not know the form of that many body interaction. Okay, so basically we cannot use this Hessian. Okay, after that we define one more Hessian and we failed. The third Hessian we found to be useful is this one, which is the inverse of the covariance matrix appropriately scaled by temperature, and the element of the covariance matrix is given by this. Okay. And now the limitation on tau is same as before. Tau should be sufficiently large so that the element of this matrix are converged, and at the same time tau should be sufficiently smaller than tau g so that the cage structure remains intact. Okay. Now Now, one important point to note here that zero temperature Hessian explicitly depend on bare interaction potential or the form of interaction. Okay, whereas the finite temperature Hessian does not explicitly depend on the form of interaction. This is the result. These are the results which I have produced by using H3. So when there is a stress drop, the eigenvalue, first eigenvalue associated with this Hessian approaches to 0. Okay, and here I have plotted the first eigenvalue non-affine displacement field associated with this stress drop and the first eigenvalue associated with this first eigenfunction associated with this eigenvalue together. As you see, they are in good agreement and the coefficient of agreement is 0.992. So basically one can use the zero temperature Hessian method to study the plastic instabilities and finite temperature, but what you need is a new Hessian. So the zero temperature Hessian definition of Hessian doesn't work. You need a new definition. You need a new Hessian at finite temperature. Now let us move to the third part, vibrational density of state. Density of state plays important role in determining many mechanical, thermal, and transport properties of amorphous system. A typical amorphous solid like this where a given particle interacts with many of its neighbors depending upon range of interaction, solving for characteristic frequencies omega for such a system is equivalent to solving a couple harmonic oscillator problem where a given mass interacts with different masses connected by springs of different spring constant. Now, solving a couple harmonic oscillator problem is equivalent to solving an eigenvalue problem, H psi equal to omega square psi, where H is the dynamical matrix or Hessian matrix of the system, psi is the eigenmode of vibration, and omega is the eigenfrequency of vibration. Once we know the eigenfrequencies of vibration, we can construct the density of state. In a amorphous system, we see 4 different types of mode. We have phononic mode similar to crystal, we have quasi-localized mode, we have randomly extended mode, and we have Anderson localization mode. One can distinguish this mode by calculating something called participation ratio. Basically, participation ratio for a mode is a measure of fraction of particles that are participating in motion. For a mode at frequency omega with eigenvectors ui omega, participation ratio is given by this. Here n is the total number of particles in the system. For phononic modes, participation ratio is found to be of the order of 1. For quasi-localized mode, we define it to be below 0.1. For randomly extended mode, it is between 0.1 and 1. For Anderson localization mode, the participation ratio is below 0.1, but they appear in the very high frequency domain. These are the plot of different types of mode. In phononic mode, we have bunch of particles that are oscillating in unison are extended throughout the system. In the randomly extended mode, particles that are participating in motion are randomly placed in space. This is a picture of quasi-localized mode. This mode is neither random like a randomly extended mode nor extended like a phononic mode. And this is what we call it quasi-localized mode according to the definition of participation ratio. Okay. Now, it has been predicted almost 40 years back by these people that at temperature T equal to 0, density of low frequency quasi-localized modes follows the universal law d of omega goes omega to the power 4 irrespective of spatial dimensionality. We know that for phonons, density of state d of omega goes as omega to the power spatial dimensionality minus 1, whereas this law is true irrespective of spatial dimensionality. Also, phonon frequencies depend on system size, like phonon frequencies are inversely proportional to the system size, whereas the frequency of quasi-localized modes are independent of system size. Now, the question is, what is the origin of this universal law? First of all, quasi-localized modes in amorphous system arise due to frustration-induced internal stresses present in the amorphous system. So based on that, it has been predicted that an atom or group of atoms effectively moves in a double well potential, and this is known as two-level system model. So basically, in our system, we have two sets of oscillator. One set of oscillator is oscillating around their equilibrium position at x equal to some x0, and another set of oscillator is oscillating around their equilibrium position x equal to some x0. Okay. So in the first reconstruction of the derivation of this universal law, we consider a low frequency oscillator interacting with another oscillator which is oscillating around x equal to 0. And this is the total potential energy of the system. So first term represents the total potential energy of the low frequency oscillator with frequency omega 1 oscillating around x equal to 0, interacts with a high frequency oscillator with frequency omega 2 oscillating around x2 equal to 0, and we consider a bilinear coupling between them I1 to x1 x2. Okay, because of this coupling, there is a renormalization in the frequency, and this immediately tells that there is a critical coupling strength IC at which this low frequency oscillator becomes unstable. Now, if we set omega 1, if we set m1 to be equal to m2 equal to m and omega 2 equal to omega dy, that is the highest frequency an oscillator can have in a system, so we immediately get a upper critical cutoff value omega c for the low frequency oscillator, which look like this. And one can rewrite it to be like this. Our task is to calculate the density of state. So this is the what it look like when we insert everything. It turns out to be proportional to omega, provided these integrals are converged. In the secondary construction, now we will consider the interaction with the other oscillators whose equilibrium positions are shifted to some x0. Basically, they create a random static force on each quasi-localized node, and that is given by this. Basically, the effective interaction in which the oscillator moves is this. So this is the potential energy, bare potential energy. This is the additional term we put for the stability purposes, and this is the forcing term. Now, because of this forcing, there is again renormalization in the frequency as well as shift in the equilibrium position. To calculate the density of state, what we need to know is the distribution of these forces. Okay, so I'm not going into the details of this calculation, but it turns out to be that this distribution of force is Lorentzian in nature with variance delta f, and when we insert this into this formula, so we end up with this. Now, without solving this integral, what we do variable transformation and we extract the omega dependence, and it turns out to be proportional to omega to the power 4, and this dimensionless integral enters into this prefactor E. Now, the first numerical verification of this universal law came in the year 2018 by Captain et al. They have studied density of low frequency states in amorphous solids at temperature T equal to 0 in spatial dimensionality T equal to 2, 3, and 4 with short range interaction. I have studied density of states in amorphous solids at temperature T equal to 0 with long range interaction, that is the charged granular matter case, in a spatial dimensionality D equal to 3. As we are working at temperature T equal to 0 in equilibrium, we have well-defined particle configuration, and knowing that, we can construct the Hessian matrix or the dynamical matrix of the system, which is the double derivative of total potential energy with respect to particle coordinates evaluated at the equilibrium positions. Once we diagonalize this matrix, we get characteristic frequencies. Once we have the characteristic frequencies, we can construct the density of state. Clearly, density of low frequency states follows the universal law d of omega versus omega to the power 4, similar to the short range interaction for the case with long range interaction in d equal to 3. Now, if we combine the result from all these 4 papers, what we can say is that the density of low frequency quasi-localized mode follows the universal law d of omega versus omega to the power 4 is true, irrespective of spatial dimension, nature, and range of interactions at temperature T equal to 0. Now, the question remains here, does this law hold true when we are at some finite temperature T not equal to 0? Because most of the soft matter experiments are performed either at low temperature or at room temperature, but not at 0 temperature. To study the density of states in amorphous solids at finite temperature T, we use the same model. Okay, our working temperature is T equal to 0.1, so that is 1/3 of Tg. We chose the number of particles in the system to be 8,000 in a spatial dimensionality D equal to 3. So basically, we have 24,000 degrees of freedom. We generate particle trajectories by using Monte Carlo simulation in NVT ensemble, that is canonical ensemble. And knowing the particle trajectories, we construct the element of the covariance matrix. And we guarantee the convergence of the elements of this covariance matrix by averaging over 6 into 10 to the power 5 Monte Carlo steps. Now, without constructing this Hessian matrix, what we do, we diagonalize this matrix. And then the eigenvalues of this Hessian is related to the eigenvalue of this covariance matrix by this formula. Okay, we take a square root of this quantity to get the characteristic frequencies. Once we have the characteristic frequencies, we can construct the density of state. Okay, and this result is obtained by using by averaging over 5,000 ensemble. Clearly, the density of low frequency states at finite temperature T equal to 0.1 follows the universal law d of omega causes omega to the power 4, similar to the 0 temperature case. Now, the question is, does this modes are quasi-localized or not? To check that, I picked a mode from this universal domain with frequency that lie below omega equal to 1. So I picked a mode at frequency omega equal to 0.56 with participation ratio 2.65 into 10 to the power minus 2, and this is the plot of that mode. Clearly, this is a quasi-localized mode. Now we can say that the density of low frequency quasi-localized mode at finite temperature T equal to 0.1 or 1/3 of Tg also follows the universal law d of omega causes omega to the power 4. Now the other questions are like, does this law hold true irrespective of nature and range of interaction? Answer is yes, because the Hessian we have used, that is inverse of the covariance matrix, does not explicitly depend on nature and range of interaction. So for us, it is quite straightforward to claim that this law holds true irrespective of nature and range of interaction. What about spatial dimensionality? The result I am showing you here is in d equal to 3. We have checked the validity in d equal to 2. It works. We count it works. We have not checked in d equal to 4, but we believe it will work even in d equal to 4 as long as the temperature of the system is less than the class transition temperature. And this work has been published recently in this paper. So the main conclusion of this paper is that our study increased the domain of applicability of this universal law. Earlier, people used to believe that this is true only at temperature T equal to 0, but our study shows that this is valid even at finite temperature T less than Tg. Now let us conclude my talk with a summary. So what I talked about is this is the plastic instabilities in charged granular system at temperature T equal to 0 under different staining mechanisms. Hessian, which is double derivative of total potential energy evaluated at the equilibrium configurations, describes those plastic events. And then I have extended that study to finite temperature amorphous systems. So stable time average configurations of amorphous system at temperature T less than Tg shows sharp plastic instabilities under simple shear deformation, and the Hessian S3, which is obtained by inverting the covariance matrix, appropriately describes those plastic events. And then I have studied density of low frequency states in charged granular system at temperature T equal to 0, which conforms to the universal law d of omega goes as omega to the power 4, known to be valid for short range interaction. Okay, and then I have extended this study to finite temperature amorphous system, which also conforms to the universal law d of omega goes as omega to the power 4, increasing the domain of its applicability.